you see how inconvenient it is without electricity. Okay. Now you see how inconvenient it is without electricity. Whew, that was rough. That is how inconvenient it is without lights. No, it was just a light tweak. Anyway, welcome to Jagan's channel. Today's science video is about, speaking of lights, electricity. So these electrical devices around us, lights, refrigerators, toasters, TV, blenders, even washing machines, those all need energy. Same with us. We need energy, but we eat. We eat to get that energy. We eat good, healthy food to perform all our tasks in our daily lives. Same with electrical devices. Electrical devices need energy. But what is that energy? That energy is electricity. But I wonder, where does electricity come from? Let me think. Oh, yeah. When you plug in your devices, it magically appears. The light magically goes on. See, come on. Hey, follow me. So this right here is a socket. So when I plug the wire in, very hard to plug things in, the light magically glows. But how? How? So in these walls are wires which connect to long, lengthy wires, and if we follow those long, lengthy wires, we'll end up at power plants. So power plants, they generate electricity. So how? By huge waterfalls, hydropower. Howling winds, wind power. Scorching sunlight, solar power. These all have enough energy to make electricity. Then from there, they go to these long, lengthy wires along the road, the poles. Have you ever seen those in your city? If not, I'm telling you right now. So, all those decrease and increase the voltage. There are, over there in those poles where the wires are, there are these tools called transformers. They increase and decrease the voltage of the electricity. And they go into underground tubes which lead to factories, hospitals, subways, stores, and even houses, including my house. Then they connect into your appliances, and as I said before, those long lengthy wires carry to the shorter wires, which then go into your socket, and when you plug it in, it goes into your electric device. Come on, follow me. I'll show you those long lengthy wires that connect to the poles on our street. Woohoo! Oh, okay. See, those long lengthy wires, that's what I was talking about. You see that middle one, the second one? Those rectangular box shaped things, those are transformers. They increase and decrease the voltage of electricity on the way to my house. And your house too. Let's head back to the YouTube site. So in the previous section, we talked about the basics of electricity. Where does it come from? What would it be like without electricity? So in this section, I'm going to be talking about atoms. Atoms are in this plastic. Atoms are in this balloon. Atoms are in me. Atoms are in you. Atoms are in the mountains, water, leaves, air. Atoms are in the entire universe. The entire universe is made of atoms. And there are different atoms for different substances. That's why there are different substances. For example, air, apples, and toys. They all are different substances, so they have different atoms. So, what does this have to do with electricity? Why am I talking about atoms? Well, here's the reason. Atoms have three parts. Electrons, which are negatively charged, protons, which are positively charged, and neutrons, which have no charge at all. They're just neutral. So, protons and neutrons are squeezed together in what they call the nucleus, in what scientists call nucleus. But the electrons are just orbiting around it in rings called shells or orbitals. I'm going to give you a visual of the atom. If you were to look at it this size, you would see this. So the protons and neutrons are crowded together in the nucleus. Think of it as the solar system. So this is the sun, and these are planets. So now there are two shells or orbitals. Just a sec. Okay. So there are two shells or orbitals which the electrons orbit. So there are two shells for this particular atom. In the second shell, there is a free electron. A free electron is an electron that is free, going to. So it's in this orbit, it orbits around, then jumps to another atom, then jumps to another atom. See? That's why it's always free. It's called a free electron because it's always free. So when the electron jumps over in this atom, then you're left with a nicely done positively charged ion. What is an ion? An ion is an atom that gains or loses electrons. So this one is positive charges because there's 3 positive charge and 2 negative charge. So the protons are more than the electrons, so it's positive charge. Meanwhile, over here, the positive charge is totally outnumbered by the negative charge particles. So this one is negative charge. That is my visual about atoms. See over there? It says hydrogen. Just for you to see. I just brought it over here so that I can see. So here's the atomic number. It shows how many protons are there and electrons. Protons and electrons. But this number is called the atomic mass. It shows how many protons and neutrons added together equals atomic mass. So, the atomic mass is proton plus neutron. So if you were to subtract the atomic mass from the atomic number, you would get the number of neutrons. In this case, 0. The name, you of course should know this, the name of element. Hydrogen. That's the name. Easy. But the symbol, the chemical symbol. Chemical symbol is the symbol for the name. So now I'm going to tell oxygen in atomic form. This will help you to draw elements in the atomic form. So protons are 8 because atomic number identifies both protons and electrons. So atomic number is 8. So protons and electrons are 8. Neutrons are also 8. 8. Because the atomic mass identifies both neutrons and protons. So if we subtract the atomic mass minus the atomic number, or the number of protons, then we would find the answer of neutrons. So 16 minus 8 equals 8. So till the 18th element, which is argon, for the first shell, it can hold the maximum of 2 electrons, and for the second shell, it can hold a maximum of 8 electrons. So we need the number of 8 electrons. So the first shell, it has to be done before we move on to the next shell. But how can it have 2 shells? How can oxygen have 2 shells? Why can't it have just 1 shell? Because in the periodic chart, the first row has 1 shell. The second row has 2 shells. So oxygen is in the second row of the periodic table chart. So for that it has 2 shells. So the first shell can have 2, the second shell can have 8 till argon. But how can we get 2 and 8? Why can't it be just 3 and 9? Because the 2 times shell number, that means 2 squared. So this equals 4, and 2 times 4 equals 8. So now, how can we fit 8 electrons into this orbital? So we have 1 electron, 2 electron. This is done because first shell can only hold 2. 3 electron, 4 electron, 5 electron, 6 electron, 7 electron, 8 electron. So why can't there just be 8 electrons in the second shell? Because that would equal 10, and that's way too much. So we have 8 electrons. I hope that makes sense now. So now we start the third section of our electricity video, static electricity. So all these things in nature, lightning, big lightning, and when you're touching people, you get shocked, right? Or doorknobs, after you rub wool carpet, after you rub your feet on a wool carpet, you touch the door and you get a shock, right? Where does this all come from? Static electricity. What is static electricity? Static electricity is the buildup of electrical charges on an object. Let me show you an example. So I cut out a grocery bag and cut it out into a small strip of plastic cover, and all you have to do is rub it 1 or 2 times fully with your pointer finger and thumb, and put your hand near it. See, it sticks. But why? See, when I rub it, negative charges from my hand are going to the neutral charged plastic cut. So now it becomes negatively charged, and this becomes positively charged. So when I put it near when I put my hand near the plastic cover, it attracts, because we all know positive and negative attract, opposite sides attract. I have 2 sets of plastic cover. So let me rub the first one. Now the second one. Okay, now see. When both of these are touched close when both of these are touched close together, they are repelling. Why? Don't take my electrons, dude. Okay, so both are negative charge because when I rubbed it, the negative charge particles from my hand gone into both plastic covers. Then when I put it together, we all know that same charges repel. Negative charge repel. Hey, don't take my electrons! Don't take my electrons, plastic! So, here's another experiment with a balloon and a napkin. Note for you guys, these experiments don't need parent supervision. You can try it at home. You can try both projects at home. See, all you need is a balloon and a piece of paper or a napkin. So, look, I'm rubbing the balloon against my hair. Now, it attracts. When I rub the balloon against my hair, electrons from my hair jump to the balloon, move to the balloon. Then this paper is positively charged. Then when the negative charged balloon attracts the negative charged balloon attracts the positive charged paper. Cheap. Okay, so that was the static electricity. So now we're gonna have the fourth section. We're gonna talk about the fourth section, which is conductors and insulators. So, Jagan, what is a conductor? A conductor is a material, for example, a metal. A conductor is a metal or material. A conductor is a material that lets electricity flow through it easily. They conduct the electricity. Remember it like that. One of the greatest conductors is copper, even though the greatest is silver. The greatest conductors always have a free electron in their outermost shell. So let's look at copper here. Copper has 29 protons in the nucleus, 29 electrons, and 34 neutrons. So, this is copper's sign. So we have 2, first shell 2, second shell 1, 2, 3, 4, 5, 6, 7, 8, 8, third 18, note to self or note to you all. And a shell can't be the element unless the shell is all full. So it can't be 9 and 10. It can only be 18 because it has to be full, and then 1. So speaking of that, here is the current flow. So this is a copper wire, conductor wire. So it flows into this copper wire. There's this push, there's this energy that lets the free electrons go to each atom. The force of the push lets free seeds like this. Then another free electron. Then another free electron. Then that one goes to here, and that one goes to here. It's like that. The push just triggers all the free electrons to move to each atom. Very fast indeed. So Benjamin Franklin thought there was some sort of fluid going from positive to negative. He thought it was from highest to lowest potential. Until J.J. Thomson figured the discovery of the electron, Benjamin Franklin thought it was a fluid. J.J. Thomson discovered that the electrons were moving from one atom to another. So that is a conductor. But what is an insulator? Insulators are the opposite of conductors, which means they do not let electricity flow through the material easily. So some insulators we can name are plastic, rock, stone, rubber. That is a very good insulator. So insulators can actually help us. Think of an insulator as a boring party guest. It's not giving that electron excitement for the party. So insulators can actually help us. So there's this copper wire. Insulators, like this plastic insulator, covers the copper wire because if we touch the copper wire itself, it could harm us. So that is recovered by the plastic insulator rubber around the wire, so that we can safely touch it. If the wire is bare, do not ever touch it. If the insulator broke like this or something like that at least, do not touch it. So till now, we've been learning about conductors and insulators. You must have gotten an idea about how they work and how they are important. If we didn't have conductors, we would get no electricity, right? Because we wouldn't have wires, those long lengthy wires I showed you at the beginning at the video. We went outside and we saw those poles. Those long lengthy wires wouldn't be able to carry the electricity to our house. Same thing with insulators. If we didn't have insulators, we wouldn't be able to be safe with electricity. And we wouldn't be able to turn off the lights, turn off the switch. So, there is another thing called electronic devices. Those include TVs, computers, laptops, iPads, phones, etc., etc. So those use semiconductors. What are semiconductors? Well, I'll tell you. Semiconductors, I would refer to them as the seeds of electronic devices. They're used in all the electronic devices. If we didn't have semiconductors, we wouldn't have all these phones and iPads and TVs and computers. So, the best element example of a semiconductor is silicon, which is found in sand. Now you learned about conductors, insulators, and semiconductors, and how they are important to us. So, there is one more thing. What is a superconductor? A superconductor has no resistance to electric current. The best example of a superconductor in elements in the periodic table is mercury. They work only when it is in very, very cold temperatures, below 0 degrees. Some examples of superconductors are MRI machines, which doctors use to examine people and their digestive problems, heartbeat problems, lungs and brain, etc. And they're also used in those hovering trains. So that is conductors and insulators section. So here I made a circuit, snap circuit. So we're gonna play a game after I demonstrate the parts of the circuit. So these are the batteries over here. Batteries are containers that store electrical charges. Remember that this is the negative side, this is the positive side. Electrons always flow from the negative side to the positive side. Always remember that. Next, we have the switch. The switch helps us disconnect and connect the current. When I press the button on the switch, the current is connected. But when I do not press the button on the switch, the current is disconnected. Now we have the bulb or the load. Load is something that uses electricity. It can be anything. It can be like a computer, an iPad, a TV. When I press it, it lights. Because the electrons can go through the switch, through the snap circuit, and go in the light bulb and light it. Finally, it goes back to the positive side. Just visualize these blue things as wires. On the bottom, there are metals, good conductors. Now we're gonna play the game. Guess which? So, we don't need a pencil. So, instead of this wire, we will do either one, the key or the eraser. And you have to guess which is the conductor and which is the insulator. So now, let's try the key first. Let's put it over here. This key is made of metal. See, it lights. I'll give you 5 seconds to think. Time's up. If you guessed insulator, you are wrong. Because this is a conductor and it can let electrons flow through the key easily. Now let's try the eraser. Oops. Why is it not lighting up? Is it a conductor or an insulator? Time's up. If you guessed conductor, you're wrong. Because this is rubber. And rubber is one of those good insulators that cannot let electrons go through this eraser. So if you guessed insulator, good job. So that's the end of the game. Now we're going to start the 6th section of our electricity video. The generation of electricity. So, first thing first, what is energy? Energy is the ability to do work. So, energy lights up your house, electricity. Energy takes form of fuel for making buses and vehicles to go. You get energy from the food you eat. Energy also takes place in wind, water, and motion. Like when you're flying a kite. So all these have energy in it. So energy cannot be created or destroyed, but it can be made from one form of energy to another form of energy. Like heat changes to light, light changes to something else. But at the same time, it also transfers from one place to another, like say from a banana to a human, because we eat bananas. The forms of energy we're going to talk about are solar, wind, water, hydro, geothermal, nuclear, fossil fuels, and biomass. Let's start with wind. Wind energy is created when the pressure of the air changes. When there are changes in the pressure of the air, then there is wind energy. Wind energy goes into turbines which spin to convert the wind energy into electrical energy. Now let's do solar energy. The sun creates a lot of heat and light, especially in the hottest places ever, like the desert. Hot here. So, only some fraction of that heat and light touches the surface of the earth. Solar panels, which are on that house over there, there can be a lot of solar panels in your neighborhood. If not, then picture the International Space Station. International Space Station has solar panels too to absorb the energy of the sun. If you haven't, then watch the International Space Station video on Jagan's channel. So, anyways, solar panels are machines that grasp the sun's heat and light and convert it into electrical energy. Now let's do hydro, which is basically water. So, evaporation of water vapor causes rain, which causes waterfall. Like steady water go down. The motion of water in a turbine, the turbine converts hydro energy into electrical energy. That is hydro energy. Now let's do nuclear energy. Nuclear is actually very interesting. Nuclear takes place from atoms, wink wink. Watch the second chapter if you haven't watched atoms. So there is this element called uranium. If you were to picture that in an atom form, many electrons. If you were to picture that in an atom form, and if the uranium atoms split apart, then a lot of energy would be converted. That is nuclear energy. It can be used to convert electricity. Now let's do geothermal energy. Geothermal energy is not created by the sun. Instead, it is created under the earth, the heat and steam. That's why if you see a geothermal energy book, you'll probably see a volcano. So we use the geothermal energy to make heat for buildings and make electricity. Now, what was I missing? Oh, biomass. Biomass is like the things that have used the solar energy. For example, wood. What else? Even food scraps. What else? Grass, planes. All those can be burnt to make electricity. Heat, then electricity. So, now last but not least, we forgot one more thing. Fossil fuels. So here's how fossil fuel was created. So back way before the dinosaurs, there was still this fossil fuels. These plants and animals are using the energy, and when they died, they were buried against huge layers of sand, rock, and mud. As the solar energy is being squeezed and squeezed. It's becoming smaller until it finally turns into in the inner layer of the dirt, it transforms into oil, which is a liquid, coal, which is a black rock, mostly used for trains, and natural gas, which is natural gas. That is fossil fuels. Now, let's talk about renewable and non-renewable energy. Renewable contains solar, wind, hydro, geothermal, what else, and biomass. So, renewable energy never runs out. Like if you have some solar panels at your house, then you would never run out of electricity because the sun's light is always there in the day. That is renewable energy. Scientists are trying to use renewable energy, and one island already gone over that challenge. It still uses renewable energy today. It's an island in the middle of Denmark, not Denmark from the United States, from Europe. It's called Samso. Samso built huge windmills first because they had a lot of wind. They were in the middle of the ocean, so that's why it was always windy there. So they built a lot of windmills. Then they moved on, so that they got more and more renewable energy. On the other hand, non-renewable energy is the opposite of renewable energy. Once you use it, it's done. You can't get any more. So, examples are the fossil fuels, oil, coal, and natural gas. So, in order to be converted into electricity, these energies, solar, hydro, wind, have to be going through different processes to be converted into electricity. So, solar it can easily be turned into electricity because of the solar panels. But the wind, water, and geothermal energy has to be spinned in a turbine. Then go into a generator. A generator is a machine that converts mechanical energy into electrical energy. And inside this generator is coils of copper wires. They spin around a magnet. And the electrons can go easily in the electric current, which is what we call an electric current. So it generates the electricity from mechanical to electric. So we talked about wind, water, and geothermal. It has to go to the turbine and generator. But the biomasses and fossil fuels, they have to be heated up, and they create steam. Then they spin to the turbine and generator. But last but not least, the uranium. The atom splits. Then it goes into steam, which goes into the turbine, and then the generator. And there you have it, electricity. So after the power plant generates the electricity, it goes through the poles, the ones that I showed you at the beginning, those long lengthy wires. But before that, the electricity leaves the power plant at about 25,000 volts. But another transformer increases the voltage to about 400,000 volts. That's enough to blow out your appliances, but it's not enough to carry the electricity down the poles, long lengthy wires. So it keeps going until it meets another transformer. That transformer decreases the voltage to safe levels so that your appliances will not blow up. Lastly, it enters your home through the socket. Then it carries the electricity back to the power plant. That is the path of electricity, and that is the end of section 6. This is the end of electricity video part 1, but in the electricity video part 2, guess what I'm going to be talking about? Batteries, circuits, components, and more. See you on electricity video part 2.